In this section, we are going to study the first-order approximation for the CPM control. We are going to introduce the algebraic method to analyze and derive the equivalent circuit model of the CPM controller. So first method we are going to talk about is algebraic method. So here we utilize the buck boost example. So buck boost. CPM example to show you that how can we utilize algebraic method to derive its CPM model. So first I plot the topology of the buck boost converter. So here is the input voltage, and here is the transistor Q, and here is the inductor L, and here is the diode D, and the filtering capacitor C, and in parallel with C is the load resistor R, and output voltage is denoted as Vt. And also there are several quantities we care about, right? One is the transistor current, IQ, T. The other one is the inductor current, IL, T. So based on the buck boost circuit, right? So actually previously we have derived its small signal model using the average method, right? Average method. So for here, I will just copy the results we have derived in the previous lecture for the buck boost topology. So basically, we have three equations to describe the small signal model of the buck boost topology. The first one is regarding the inductor voltage equation, right? So L dIL over dt small signal equals to D times the input voltage small signal plus D prime times output voltage small signal plus Vg minus V times the duty cycle signal. And second formula is about the capacitor current equation. So the C times dV over dt equals to minus D prime times IL, small signal, minus output voltage divided by the load resistor, which is the resistor current. And third one is the inductor current times small signal duty cycle. And the third equation is about the input port, right? Input port, we have the kind of the KCL, right? Input current small signal equals to D times IL plus IL times duty cycle. Okay, so those are the three models, right? Three small signal models we have previously derived for the PWM control, right? So now let's look at what happens, what changes can we have for the CPM control. So for this section, we are going to first introduce an approximation method for analyzing the CPM control, which we call it as first-order model approximation. So the concept is pretty simple. So here I'd like to plot the figure to show you. So in time domain, we plot the waveforms for controlling current, IC, and the inductor current IL. So IL will be piecewise linear, right? So when the switch is on, the IL will rise linearly. When the IL hits the IC, switch is off. The latch is reset, so IL begins to drop linearly. And then here is the next switching cycle, right? TS. So that's the general waveform. And here is the mode 1 ending point, so D times TS. So the first order model approximation means that we approximate the IL is equal to IC. So we consider that the IL average is equal to controlling current. So this is accurate when the converter operates in CCM. And when the artificial ramp is small. So we will literally introduce the ramp. Here, you just need to know that when the artificial ramp is small. So well in CCM means that inductor is large, inductor ripple is small, right? So we can approximately consider that IL average equals to IC. And based on this approximation, we can derive that the small signal IL is also approximately equal to small signal IC. In S domain. So therefore, if we consider that this approximation is valid, then we can replace the IL small signal by IC, right? So I will replace them directly. C. All right, so then we can do the following step, right? So here is in time domain, we can convert this into Laplace domain, right? So S domain. So we do the Laplace transform. Okay, so here is also IC. So we do the Laplace transform to these three equations so that we can see that top one, the derivative in S domain will be equals to L times L, IC, S. On the right-hand side is D times VG, S plus D prime, VS plus V minus V, D small signal S. For the second capacitor equation, similar, the derivatives Laplace transform will be S times C V S equals to minus D prime IC S minus V S over R plus IL. Third one, relatively simple because we don't have any derivative or integral part, right? So we just convert the T to S. Then we can process this group of formulas. We mark them by 1, 2, 3 to easily process them. So first we deal with the equation 1. So from equation 1, we can find out the expression for duty cycle D. So which is a fraction, right? Fraction. The denominator is the Vg minus V. And the numerator equals to the 3 terms adding or subtracting together. So SL ICS minus D Vg minus D prime Vs. So next step, we will insert the duty cycle expression into formula 2 and 3. Okay, now let's erase the left-hand side of the blackboard so I can show you the detailed derivation. Okay, we have erased the blackboard. Now let's continue to make the derivation. So before we insert this formula 2, equation 2 and 3, we first can consider the DC large signal model for buck boost topology, right? For the DC model, we know that there is a relationship between the output voltage and the input voltage. So for buck boost, the output voltage equals to input voltage times minus D over D prime. That's the voltage gain for buck boost converter. And second DC relationship is the expression for average inductor current, right? When we study the DC model, we learned that the average inductor current equals to minus V over D prime times resistance. So for D prime resistance and the output voltage, we can replace output voltage by this formula, right? So we can utilize input voltage to denote IL. So this will be equal to D over D prime square R times input voltage. Then we can also replace IL, V by those formulas. So figure out the resulting in capacitor equation. So basically this equation 2 will be transformed into this format. So equation 2 becomes SC Vs on the left-hand side. On the right-hand side, we organize the 3 parts by combining the common items together. So the first part will be the IC cap part. So its coefficient is SLD over D prime R minus D prime. And the second item is the V cap parts. So the coefficient, also we combine them together, is the D over R plus 1 over R. And the third part is the gating input voltage part, VGS. So also we combine the common items, right? Its coefficient is just here, right? D square over D prime R. That's the complete expression for the capacitor equation, right? So then we look at this expression, we can see that there are majorly 4 parts, right? Each part can be equivalent to an specific circuit, right? For example, if we look at here, so this one is basically a controlled current source behavior, right? So basically we can use a controlled current source to denote. So the controlling coefficient is the coefficient here, right? D cap. D square over D cap, D prime R, the VG small signal. And next, we look at this one, right? This one is basically a independent current source behavior. So those two components, they are in parallel. And this current source is SL D over dr minus D prime times IC, controlling current, D prime R. And next, we look at this one, right? This one means that the current is proportional to the voltage. So this is indeed a resistor behavior. The resistance will be equal to dr over d. And last one is, so actually this is a combination of two resistors, right? One is R over D and one is the load current, load resistor. So this is R. So we put them separately to better show you the feature of the circuit, right? Here is the load resistor. Here is an effective resistor with R over D. And here is the output voltage. The last one will be this part, right? This part. Last one is this part. So this part will be essentially a capacitor behavior, right? Capacitor behavior. The capacitance will be equal to C. So you will see that this circuit is equivalent to this equation, right? So we have fully established the equivalent circuit model for this equation. And next, let's look at the input current equation by inserting 1 into 3 and also combining those two into equation 3. We can find out the expression for IQ will be equal to also 3 parts, right? First part is controlling part. So the coefficient is SLD over D prime R plus D. And second part is the output voltage part. The coefficient here will be negative number, so D over R. And third part is the input voltage part. Also, we combine the coefficient will be minus D prime over D prime R, minus D square over D prime R. So using the similar manner, we can also establish its small signal circuit model. So input port will be just a input voltage source. And its current is denoted as IQS. Then we look at the 3 parts, right? This part will be modeled by an independent current source. So SL D over D prime R plus D times IC. Right? And this part will be a controlled current source, a controlled current source. So D over R VS. VS is an output port voltage. That's why we use a controlled voltage source. And last one here, right? this, again, you will see that this means that the current is proportional to the terminal voltage. So this can be modeled by a resistor whose resistance equals to D prime R over D squared. So that's the complete equivalent circuit for the input port, right? So the procedure is pretty standard as what we did before. So now we can combine them together, right? Place them together. So by placing the output port equivalent circuit on the right-hand side of the input port equivalent circuit, we can obtain the complete circuit model of the entire converter. So based on this derivation, we can introduce the canonical circuit model for CPM. So rather than using the specific coefficients expressions, we introduce certain symbols of coefficients to normalize the model. Because for canonical model, we will consider that it's applicable to different topologies, right? So here is the normalized results. Input port, right? Input port voltage. And here, input port current. We use IG. Not only for buck boost. Right? For buck boost, it is equal to IQ, but for the others, not. And here, right, current source. We denote its coefficient no longer as this complicated equation. We use F1. And here, we use R1 to denote. And here is the controlled current source. We use the G1 to denote its coefficients. Then we plot the output port equivalent circuit. So here is another controlled current source. We denote as G2 VG. And here is the independent current source. We denote as F2. And resistor, right? R2. Capacitor C. And load resistor R. Output voltage. So that's the canonical model for CPM control. And basically, different topologies, they have the unified model, but different combination of the coefficient. So in our textbooks, there is a table which shows you the detailed expressions for different topologies coefficient. You can check it for future usage. Okay, so in this section, we utilize the example of the buck boost converter, and we use the algebraic method to derive and establish the first order model for CPM controller. And next, we are going to talk about how can we derive the transfer function of the CPM controller.